through the algorithm, which can be annoying at best and impossible at worst. Because it could be impossible, essentially, I don't know if it'd ever be impossible, but it could be so intractable that it's essentially impossible. Because this is a fairly simple constitutive model. They can get far more complex, right? And you have pressure dependence and all this other stuff. It can be just almost basically intractable to try to derive the consistent tangent moduli and then code it all up, right? So what's often done in practice is to use some sort of finite differencing. Right? So in other words, our residual, or the tangent stiffness is this. Right? So what we do is evaluate the residual at u plus some perturbation of EI minus perturbation at u all over h, right? So this would be like a forward difference calculation where EI is a perturbation vector on the degrees of freedom. So in other words, if you had a million by million matrix, your first EI would be, well, I goes from 1 to a million, first of all. And your first EI would be 1, 0, 0, 0, 0, 0, 0, 0, 0, all the way to a million. And your second one would be 0, 1, 0, 0, 0, 0, 0, 0. Your third one would be 0, 0, 1. Right? And so you have to do a million perturbations, because each perturbation would be one column of the tangent stiffness matrix. So if you did it this way, you'd have to do a million perturbations just to construct the tangent stiffness matrix. And you have to construct the tangent stiffness matrix every Newton iteration to preserve quadratic convergence. Not fun. Right? So it's not often that we actually do that either. Right? There's things we can do to improve it. First thing we could do is this not, and it's a sort of minor improvement, but the one thing we could do is not actually do the perturbation. Use automatic differentiation. We talked about this last time. Right? So there are computer algorithms that can sort of construct what the derivatives are going to be via the computer implementation of the chain rule. This is the best way to do it because it gives you machine precision, exact, consistent tangent moduli. Okay. Problem is that there is something you have to run it through an algorithm, so it doesn't save a lot, although it can greatly save on round-off or inaccuracies that can be introduced, because that derivative, like all finite differences, right, that derivative is most accurate when h is small. But if I make h really tiny in a computer, I have over on the left u plus he, I compute a residual, and then I compute, I guess that should be partial u, r, right? I also compute a residual here, but those two numbers are really close to one another if h is small, and you get the errors introduced by subtractive cancellation, right? So you want h to be small, but not too small. Small enough to be accurate, but not small enough, so small that you get numerical instabilities. And so choosing h is difficult, right? Knowing what the correct perturbation size would be. Okay, so that's another sort of advantage. With automatic differentiation, you don't have to worry about that. You get numerically exact derivatives. But it doesn't resolve the other problem, even with automatic differentiation, is that, essentially we want the derivative with respect to every single degree of freedom change. We want the derivative with respect to a change in every single degree of freedom. So even if we're using automatic differentiation, we would still have to compute the derivatives for changing every, you still have to do it a million times. Right? So we wouldn't have subtractive cancellation, we'd have accurate derivatives, but we still have to do it a million times. We don't like that either. So, and this really, we're not going to cover the details of these kind of things in class. I'm just trying to make you aware of some things you can do Let's look at a 1D system. In a 1D system, in a 1D system, if I'm going to go about constructing this via tangent, this sort of approximation, I'm going to perturb every degree of freedom in isolation, right? So I'm going to perturb this degree of freedom and compute the residual and the unperturbed residual, subtract the two, and that's going to be my first column, okay? But my residual, if I perturb this node, and I have linear basis functions that are like this, right? If I perturb this node over here, how far along is it going? I mean, how many non-zero entries am I going to have in that column? Right. Just two, and if the far left-hand side, just two, right? If I perturb that node, it only changes the force in the one next to it, right? If I go over here and I perturb this node, how many is it going to change? 3 in that case, right? One to the left, the one to the right, and the one to the right. Right? And we know this when we look at the matrix in a 1D system. It's tridiagonal, right? So every column is just got zeros, and then one above the diagonal, one below the diagonal, right? That are non-zero. So if I'm smart, I could say perturb this node and this node and this node and this node all at the same time. So now my E would be like 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Right? And my residuals that would come back would be fully populated. There'd be no zeros in it. Right? It'd be fully populated. Okay? So I always feel obligated to look at my phone during class because they text us if there's an emergency or something, you know. So that's why I always glance at it if I get a text or something. Yeah, so if I'm smart, I could perturb all of those at the same time, and they wouldn't interfere with each other. And if I'm just smart about the bookkeeping, I can construct the tangent stiffness, right? I take those 3 nodes and I put them into their proper place in the matrix, and I take the contributions from those 3 and I put them in theirs, and I put them in theirs, right? And it's not, the bookkeeping is not trivial, but it can be done, all right? In 1D, it's actually not that hard, but the trick is now we go to 3D or 2D, right? Where the connectivities aren't so obvious in terms of where the rows and columns are in the tangent stiffness matrix. And so really what we use here is graph theory. So you can use graph theory to construct adjacency matrices, and it's an understanding of the connection, and then you can use that to do what's called coloring. So in other words, what you're going to do is you're going to go down the list of nodes, and you're going to color every node that you could perturb in isolation. So like I might color this one blue, this one blue, this one blue, and this one blue, and I can color all of those, right? Now really in a computer we don't use colors, we use numbers, so those would be all assigned to number 1, right? Then I could also perturb this one, this one, this one, and this one, so I'd color those red. And then I could perturb this one, and this one, so I'd color those orange, okay? So basically, I can construct the whole tangent stiffness matrix with just 3 perturbations. It's actually always true in 1D. In 1D, if you have a billion by a billion system, you can construct the entire tangent stiffness if you understand the connectivities with only 3 perturbations. That's way better than doing a billion perturbations, right? But 3s are better than a billion, right? A little bit? Okay. So the problem is when you go to 2 and 3D, it's much, much harder. We have to use graph theory, and we use coloring algorithms. So there's actually algorithms that can color, based on the connectivities of 3D matrices, can construct these colorings, okay, so that you can do the perturbations like that, and you can get it way down, okay, way down. The problem is in 2 and 3D or in big, large graphs, there's no perfect algorithm. In other words, in 1D, we can always get it down to the minimum set, 3. Okay. With big graphs and lots of complex connectivities, there's no perfect algorithm to get the minimal set. There's algorithms that do better but take longer, right? So it's another trade-off. Like one of them is called the greedy algorithm, greedy coloring. So there's different algorithms we can use, and it's all a trade-off between, do we want the minimal set so that we do the minimal perturbations on the tangent stiffness at the expense of taking longer to do the coloring? Right? Good thing is we only have to do the coloring once. It's sort of an initialization. Unless you change the connectivity, right? So unless you remesh or use it, or you're doing extended finite elements or adding nodes or something like that, for the most part, if the structure of the mesh never changes, you just do the coloring once. So in that case, it's worth spending a little more time getting the minimal set of perturbations, because the perturbations you have to do every time, right? Every time through the Newton method. Okay.
Or if you reuse the mesh.
Yeah. If your mesh doesn't change, then the coloring doesn't change, and so it's fine. All right. So that's just something to be aware of. We're not going to do anything with that in the class, but there are libraries out there, like in Trilinos, which is a big scientific software language, that can do coloring for you. And in our experience with codes that we've used, that say you have 1,000,000 degrees of freedom where you'd have to do 1,000,000 perturbations, you can get that down to like 30. 30 is better than 1,000,000, right? And it's way faster. Okay. The other thing you can do to save yourself some time is you give up the quadratic convergence by not reconstructing the tangent every step. Okay. So in other words, you could reconstruct the tangent only every 10 iterations or every 100 iterations. And the idea there is that the individual Newton iterations are just, they're like the Gauss-Seidel iterations. They're just matrix vector multiplications, right? So what you can do is you can, construct your tangent stiffness and then take it through several Gauss-Seidel iterations and then at some point reconstruct, and at some point reconstruct, right? If you reconstruct it every time, you're going to have quadratic convergence. But the construction process takes longer. So here you're giving up, you're going to take more iterations, but you don't have to construct the tangent stiffness. And so there's games you can play there with, okay, I'm going to give up the quadratic convergence, but I'm not going to have to construct the tangent stiffness, so that's going to save me overall time.
How you can find out that you get the convergence?
Well, if it's reducing the residual. And in fact, if you write in your own algorithm, it's in fact what you do is maybe you set some maximum number, like 10, but if it's not converging, you have to reconstruct it. So you'd have smart, so you're going to say, okay, I'm always going to reconstruct after 10 unless I'm not converging, right? If the residual is, and you could have some heuristics in there to say, if it doesn't reduce by some amount, by at least 10%, then I'm going to reconstruct. Or certainly if it gets bigger, right? If the residual's blowing up instead of getting smaller, then you just want to reconstruct, right? Reconstruct the tangent stiffness with the new displacement. So those are all games you can play. And so next time on Monday, I've got some code that I wrote. It's a single element, but it has got a plasticity model. And we'll just sort of go line by line, and I'll show you exactly what's going on, and we'll kind of go. It's these equations, but coded up, and we'll look at them because eventually you're going to have to modify that or write your own. So, okay.